Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the singularity function of this course. So the learning objectives of today's lecture are: what is singularity function? So first we will define the singularity function. Then what are the different types of singularity functions that are being used? And basically they are step function, ramp function, impulse function, and the unit doublet function. So these are the four types of singularity function. We are going to discuss in detail about these four functions. Then we'll also discuss the Laplace transform of these singularity functions, and in the last we will discuss the relationship between singularity functions. So what is singularity function? If the function and or their derivatives are discontinuous, then these functions are called singularity functions. And the point at which these functions are discontinuous are called singularity functions. So there are two terms, one is the singularity function and other one is the singularity point. The point at which these functions are discontinuous are called the singularity function. And the commonly used singularity functions are step function, ramp, impulse, and unit doublet. So these are the generally used impulse functions. So we'll take one by one. So first is, what is unit step function? So unit step function is a function whose value changes from 0 to 1 in 0 time. So mathematically we can write ut. It is unit function is denoted by ut. It is denoted by ut. It is denoted by ut. So mathematically it can be written as ut is equal to 1 for t greater than 0, and it is 0 for t less than 0. This function is not defined at t is equal to 0. So we can say that this function is discontinuous at t is equal to 0. So graphically we can represent unit step function as like this. This one should be here. So this region is called t greater than 0, and this region is called your t less than 0. So we can see that it values changes from one level, usually 0, to another level, which is 1 in 0 time. So this is the definition of unit step. This is the mathematical expression, and this is the graphical representation of unit step function. So we can have, this is the basically reflected unit step function. If we for u minus t. So time reversal, it is u plus t, it is u minus t. So this t greater than 0, it is 0, and t less than 0, its value is 1. So u minus t is defined for minus infinity to 0. So for t less than 0, its value is 1, and t greater than 0, its value is 0. We can also, this is the time reversal, this is the amplitude reversal. So this is basically minus ut. So this is minus ut function. So these are the graphical representation of unit step function. Suppose we want to just draw this function, say this function. So it is, suppose it is a time, so it is tau, so it is ut minus tau. So its value is 1 for t greater than tau, and 0 for t less than tau. Its value is 0. So this way we can just apply the operation. So it is the shifting operation on unit step. So what we can conclude, the value of unit step function is 1 for a values t greater than 0, and it is 0 for all values of t less than 0. So it is undefined at t is equal to 0, means this function is discontinuous at t is equal to 0. Then unit step function has a value between 0 and 1, and this value changes suddenly at t is equal to 0. So this is another point we can conclude from this. Because of this step change in unit step function at t is equal to 0, the value of derivative of unit step function is infinite at t is equal to 0. In other words, we can say that unit step function is discontinuous at t is equal to 0. So it can be seen that derivative of unit step function is 0 at all instants except at t is equal to 0. At t is equal to 0, its value is infinite. And the t greater than 0, it is constant, magnitude is 1. So if we differentiate a constant, we get the 0 value. Now the shifting operation of unit step. So here we can see that this is the time tau. If we shift a unit step function, so we have earlier I have explained it. So this is this t is greater than tau. Its value is 1. Basically, it is 1. And t less than 0, its value is 0 value. Okay. So this is the time shifting. We can also see that, suppose, look at here. This is your time axis. This, suppose the function is ut plus tau. T plus tau. So this is the basically delayed. This is the delayed. We can say the delayed shift. Okay. So the graph of this ut plus tau will be like this. So it will start from t tau. This is 0. So this is minus tau. So basically ut plus tau is nothing but it is ut minus tau. So it is called advanced. So in place of starting at t is equal to 0, it is starting minus t plus tau. So its value is 1 in this interval. So in this interval, its value is 1. Here this is 0. So this is 0 and this is the 1. So this is the shifting operation of unit step. Now come to another singularity function. This is that is the ramp. So ramp is mathematically defined. Rt is equal to t for t greater than 0 or for t less than 0. So for t less than 0, its value is 0. For t greater than 0, its value is t. So for analytical point of view, we take t greater than or equal to 0 is equal to t. So this ramp function is linearly increases with time. So this is Rt is linearly increases with time. So this is the mathematical expression, and this is the graphical representation of ramp function. So what we conclude, the ramp function has 0 value in the range defined by t less than 0. When t greater than 0, the ramp function increases linearly with time. Then unit step function as the derivative of the ramp function. So this is the relationship between unit step function and the ramp function. And alternatively, ramp function is the integral of the unit step. So later on we will prove these two relations. If we differentiate this RT, so dRT upon dt is equal to 1. So if you differentiate a ramp function, we will get the unit step function, and if we integrate a unit step function, we will get the ramp function. So these are the relationship between the ramp and step function. So this is the shifted ramp. So this is the ramp, this is the 0, and this ramp is starting at t is equal to tau. So this is the delayed ramp. Then this is the reflected ramp. So reflection means minus t, time axis, time reversal. So these are the definitions of a ramp function. Now come to the third one, impulse function. So impulse is a function whose value is 0 everywhere except at t is equal to 0. And at t is equal to 0, its value is infinite. So it is designated as delta t, also called Dirac delta function. And it is graphical representation is this. We can say that. So this region is t greater than 0 and this region is t less than 0. So everywhere its value is 0 except at t is equal to 0. At t is equal to 0, its value is infinite. So how will we define this? So if you integrate minus t delta t into dt, its value is 1. So mathematically we can define impulse function like this. So in physical realization, what we just realize a unit area impulse function, or you can say the unit impulse function. So these are the some properties of impulse function. So delta 0 at t is equal to 0, delta tends to infinity, and delta t is 0 everywhere except at t is equal to 0. So at t is not equal to 0, its value is 0. Third property we have defined. So this is the delta t into dt. If you integrate minus infinite to plus infinite, its value is 1. Because in between minus infinite to plus infinite, this function is defined at t is equal to 0. So we get this 1. And delta t is minus delta t. We can see here. This is your delta t. And this is t greater than 0 and this t less than 0. Okay. So basically it is an even function. When delta t is equal to minus delta minus t, then this is the definition. A function is said to be even function. A function is said to be, what is the definition of even function? A function is said to be even function if ft is equal to f minus t. So we can look at here, this is the delta minus t, so its value is 0 everywhere and 0, so it is mirror image, so it is an even function. So delta t impulse function is an even function. Then there is another properties. So if we integrate a function ft from minus infinity to plus infinity, and this function is multiplied by delta t, so it is 0. So f0, initial value. So we can get the initial value of the function by multiplying the function of with delta t and integrate over minus infinite to plus infinite, we get f0. And if this function is multiplied by delayed impulse function, what is delayed? Delayed means this is delta t minus t0. So this is the t0. So t greater than t0, this value 0 here, this region, and this is t less than t0, so it is 0. So this function delta t minus t0 is defined at t is equal to t0. So we get f t0. So this is the property of, and there is another property delta at. If you multiply by a constant at, then we get this. So these are the some properties of impulse function. Now double it. Now come to the relationship between the unit step function and ramp function. So if you differentiate impulse function, we get the ut. If you integrate ut, we get ramp. So we can prove that if you differentiate rt is equal to t, so dt upon dt, that is 1. If we integrate minus infinite to time t, we get t into ut. So basically, what is rt is equal to t ut. This is the relationship between ramp function and unit step function in time domain. Now, relationship between impulse and unit step. So, if you integrate impulse function over minus infinity to time t, we get the unit step. And if you differentiate unit step, we get the impulse. So, these are the relationship between these unit step, ramp and impulse function. Now come to the fourth one, unit doublet. So the derivative of unit impulse function with respect to time at any instant of time is known as unit doublet function. So this is the definition of unit doublet function. So if you take the derivative of unit impulse with respect to time at any instant of time, you get the unit doublet. So it is defined as d upon dt delta t minus t. So it is delta t minus t, and that is 0 for t not equal to 0, and it is plus infinite and minus infinite for t is equal to capital T. So the name of the function is given as doublet because, why it is called doublet? Because it can be obtained from the function shown below as a tends to 0. So we take, this is the unit area, this is the unit area of unit impulse, this is the unit area, we add, we get the doublet. So this is the graphical representation of unit doublet function with a tends to 0. So these are your singularity functions, unit step, ramp, impulse and unit doublet function. Here I can explain the Laplace transform. So we take the Laplace transform. So take the Laplace transform. So Laplace transform of ut. Okay. So Laplace transform ut. This is basically, this is the definition. Say this is the ut and e power minus st dt. Okay. So we can see that this unit step is defined for t greater than 0 and for t less than 0 its value is 0. So this integration is from 0 to infinity, and this is 1 e to power minus st dt. And if we take the difference, it is so us Laplace transform is of unit step is 1 by s. Okay. Take the Laplace transform of your rt. Again, minus infinite to plus infinite rt e to power minus st dt. So this rt is defined for t greater than 0. So its integration becomes 0 to infinity, and rt is equal to t t e to power minus st and dt. If you take the integration of this ramp function at this t into e to power minus st, it is coming 1 by s square. So this can be written as 1 by s into 1 by s. Okay. So we can write here rs is equal to 1 by s into us. Okay. And we also know that s is a differential operator. And 1 by s is a integral operator, or we can say that integrator. So s is differentiator and 1 by s is integrator. So look at here, if we integrate, so basically rs is equal to integration of unit step. Okay, so we can prove this. We can see that RT is equal to integration of unit. So we take the Laplace transform. Okay, and the Laplace transform of this this delta t. If we take the Laplace transform of this delta t, so it is minus infinity to plus infinity delta t e to power minus st dt. So it is e to power minus st at t is equal to 0. So this is 1. So if we take the Laplace transform of impulse, we get the 1 value. So look at here. So here, if we take that s into us, it is 1. So s is a differential operator. If we differentiate unit step, we get the impulse function. So these are the relationship of these singularity functions. So what we discussed today? We discussed so summary, you can summarize here. You can summarize here. Singularity functions. Step, unit step, ramp, impulse, then relationship, and third the Laplace transform. All these topics we covered today. In the next lecture, we will discuss the waveform synthesis with the help of these singularity functions. So thank you very much. Jai Hind.